Okay, so we've started with simple non-negative simple function, and then non-negative functions we define what was the integral. So you'd like to know how to compute these integrals, though we have a formal definition. So given some measures, we would like to know how to compute these various integrals. So we do some examples now. So this is integration with respect to the counting measure. Okay, so x equal to n, s is the power set of n, and mu equals counting measure. Okay, so now you define the function f from x to r. So f of k equals, so it's a sequence. A function from the natural numbers is just a sequence ak, and then we assume that this is greater or equal to 0. So now let us define fn of k equals ak for 1 less than or equal to k less than or equal to n, and 0 if k is bigger than n. Then fn is non-negative, fn is less than or equal to fn plus 1, and in fact for all n, and in fact we have fn increases to f, because fn is just a1 a2 ak, fn plus up to an, and then fn plus 1 is a1 a2 an up to an plus 1, and so on, and these are all non-negative, and therefore it's obvious that you have this. And also fn, if you see, is nothing but sigma ak chi of singleton k, k equals 1 to n, and therefore this is a non-negative simple function. Therefore integral fn d mu over x is sigma k equals 1 to n ak into measure of singleton k, it is just 1. Okay, then by the monotone convergence theorem, you have integral over x f d mu is equal to limit n tending to infinity integral over x of fn d mu, and that is nothing but sigma k equals 1 to infinity ak. So integration with respect to counting measure over n is just summation for non-negative measurable functions, and again the sum of the series need not be finite, so the integral can be infinity. Okay, so this is just summation which you have here. Next example, we will have integration with respect to the Dirac measure. What is Dirac measure? You have x naught in x, and then you have mu of e, or rather delta of e, is equal to 1 if x naught is in e, and 0 if x naught is not in. This is the Dirac measure. So we want to know what is the integration with respect to this. Okay. Okay, let me write mu itself here so that d delta will be not okay. Okay. So phi non-negative simple function. So phi is equal to sigma I equals 1 to n ai alpha I chi of ai, and let us say ai disjoint. So if x naught does not belong to ai for all 1 less than equal to I less than equal to n, then you have phi of x naught equal to 0. Also, sigma I equals 1 to n alpha I mu of ai. X naught is not in any of them, so all of these are 0. So this is equal to 0 and this is equal to phi of x naught. And that's equal to integral phi d mu. So x naught belongs to ai naught, and therefore this, so for some 1 less than equal to I naught less than equal to n, this implies that x naught does not belong to aj for all 1 less than equal to j less than equal to n, j not equal to I naught. Then what is integral over x phi d mu? This is equal to sigma I equals 1 to n alpha I mu of ai. All the other j's will be measured will be 0, only one will be of measure 1, so this is equal to alpha I naught, but this is also equal to phi of x naught from this thing. So we have, so this implies that integral over x phi d mu equals phi of x naught. Now if f is any non-negative measurable function, then phi n is a simple functions, phi n increasing to f, then you have that integral over x f d mu equals integral limit n tending to infinity phi n d mu over x, and that's equal to limit n tending to infinity phi of x naught, phi n of x naught, and that's equal to f of x naught. So integration with respect to Dirac measure concentrated at x naught is just evaluation of the function at x naught. Now let us give another example here. So let aij equals 1 to infinity be a double sequence of non-negative reals. So x you take as capital N, S equals P of n, mu equals counting measure. Define Fi evaluated at j as aij, 1 less than equal to I, j less than equal to infinity, and define f is equal to sigma I equals 1 to infinity Fi. So then what is f of j? F of j is sigma I equals 1 to infinity Fi at j, which is equal to sigma I equals 1 to infinity of aij. Now we know that integral f d mu is summation I equals 1 to infinity integral over x fi d mu. But we are now in the counting measure on the natural numbers. So what is integral f d mu? It is sigma j equals 1 to infinity f of j is equal to sigma I equals 1 to infinity of sigma j equals 1 to infinity fi of j. So if we expand this, you get sigma j equals 1 to infinity f of j, which is sigma I equals 1 to infinity of aij, is equal to sigma I equals 1 to infinity sigma j equals 1 to infinity fij is aij. Therefore, if you have a non-negative double sequence, we have proved using the methods of measure theory, and this is a well-known result in theory of summation of series. Namely, if you have a non-negative double sequence, then you can interchange the order of summation without any problem. Either both sides will be finite and will be equal, or both sides will be infinity. That is the understanding in this thing. So we have, now this is not necessarily true for arbitrary double sequences. We will see examples, and that also we will use some limit theorems from measure theory to show when you can interchange the order of summation when aij's are not necessarily non-negative. We will see that example much later. So right now, for non-negative double sequences, we have that you can interchange the order of summation without any problem. Okay.